Hello friends, in this video we will gain some insights regarding primary reformer unit which is used in petrochemical sector. Here we will learn about its process features, maintenance procedure and leading technology providers or licensors. So let us dive straight into pool of information. Disclaimer. The images used in this video are for information purposes only. They are owned by their respective licensors. What is a primary reformer? A primary reformer is a critical process unit in the petrochemical industry used to convert hydrocarbons, most commonly natural gas or methane, into hydrogen-rich synthesis gas, syngas, through a process called steam methane reforming, SMR. This syngas, a mixture primarily of hydrogen, H2, and carbon monoxide, CO, is an essential feedstock for the production of chemicals such as ammonia, methanol, and various other industrial products. The primary reformer, through its catalytic and thermal processes, is a foundational technology enabling large-scale hydrogen and syngas production, making it indispensable in the modern petrochemical industry. Key features and working principle. In the primary reformer, purified natural gas, mainly methane, is mixed with steam and passed through catalyst-filled tubes at high temperatures, typically 780 to 820 degrees Celsius, and moderate pressures. Nickel-based catalysts are commonly used to facilitate the reforming reactions. The process is highly endothermic, so heat is supplied by burning fuel in the furnace section of the reformer. Here we will throw some light upon key components of a primary reformer. A primary reformer is a complex unit with several critical components that work together to facilitate the steam methane reforming, SMR, process. The main components include reformer tubes. These are high-alloy tubes filled with catalyst, where the endothermic reforming reactions occur. The tubes are designed to withstand high temperatures and pressures, as well as thermal and mechanical stresses. Catalyst, typically nickel-based, the catalyst is packed inside the reformer tubes and is essential for promoting the chemical reactions that convert hydrocarbons and steam into syngas. Burners, located in the furnace section, burners supply the necessary heat for the highly endothermic reforming reactions by combusting fuel, usually natural gas. Furnace/firebox. It is the enclosure that houses the reformer tubes and burners, providing the high-temperature environment required for the reactions. Inlet and outlet systems manage the entry of feedstock, hydrocarbon and steam mixture, and the exit of product gases, syngas, and are designed to accommodate thermal expansion and prevent excessive mechanical stress. Radiant and convection sections. The radiant section is where the majority of heat is transferred directly to the tubes, while the convection section recovers heat from flue gases to preheat the feed or generate steam. Refractory lining. These linings insulate the furnace to minimize heat loss and protect the structure from high temperatures. Each licensor provides list of approved refractory vendors that have their own respective refractory design linings. Some of the leading refractory vendors for primary reformer are Rh.Magnesita, Vesuvius, Morgan Advanced Materials, Calderys, and AGC Pliberco. Support structures and tube sheets. These provide mechanical support and alignment for the tubes within the furnace. These components are meticulously engineered to ensure efficient heat transfer, optimal reaction conditions, and long-term mechanical integrity under harsh operating environments. The two main types of catalytic reformers used in refineries are semi-regenerative, SR, reformers and continuous catalyst regeneration, CCR, reformers. Both are designed to upgrade naphtha into high-octane reformate and produce hydrogen, but they differ significantly in operation, design, and performance. Semi-regenerative reformers operate at higher pressures to reduce coke formation, but this limits the achievable octane number and yield. The unit must be shut down periodically for catalyst regeneration, which reduces overall availability and efficiency. Continuous catalyst regeneration reformers feature a moving bed system where the catalyst is continuously withdrawn, regenerated in a separate regenerator, and returned to the reactor. This allows for lower operating pressures, higher severity operation, and greater yields of both reformate and hydrogen. CCR reformers can run for years without shutdown, making them the standard for modern, high-capacity refineries. Maintenance procedure of a primary reformer. Maintaining a primary reformer is essential to ensure safe, efficient, and reliable operation in the petrochemical industry. The maintenance procedure typically involves a combination of planned shutdown activities, ongoing inspections, cleaning, and careful startup and shutdown protocols. Furnace and burner inspection. Firstly, inspect burners and furnace box for wear, damage, and proper flame distribution. Burner tuning and maintenance ensures even heat distribution and prevent hot spots that can damage reformer tubes and ultimately the overall process. Reformer tube inspection and assessment. Regular inspection of reformer tubes for signs of coke buildup, corrosion, cracks, or thinning is performed. Advanced engineering assessments and remaining life evaluations are done in order to plan replacements or repairs ahead of failures. Cleaning of convection section and tubes. Cleaning of the convection section coils and radiant tubes is performed, which removes fouling and deposits that reduce heat transfer efficiency. This cleaning is often done during turnarounds and can involve mechanical or chemical cleaning methods. Refractory and firebrick maintenance. Inspection of refractory lining, firebricks, and coatings is done to maintain insulation and protect structural integrity from high temperatures. Any damaged section is replaced with new refractory materials. In case of a large overhaul, entire furnace refractory lining is demolished and new refractory materials are installed as per design specifications. Let us discuss about typical maintenance procedure steps in brief. Preparation. Fuel gas valves are closed and lines are purged with nitrogen. Inert gas circulation is performed to prevent oxidation during shutdown. Inspection and cleaning. Furnace and convection sections are opened. Tubes, burners, refractory, and convection coils are inspected by the process and quality engineers. Fouling deposits from tubes and coils are cleaned by appropriate methods. Repairs and replacements. Replace damaged tubes or refractory materials as needed, and burner components and control systems are repaired as per their status. Startup. Gradually heating of the furnace is done up to 350 degrees Celsius, then steam is introduced at controlled pressure. Burners are ignited sequentially to ensure even heat distribution. Temperature and pressure are increased to normal operating levels while monitoring closely. This holistic approach, combining inspection, cleaning, controlled operation, and safety protocols, ensures the primary reformer operates efficiently and safely over its service life. Major technology providers in the field of primary reformer technology, particularly for steam methane reforming, SMR, and autothermal reforming, ATR, include KBR. The KBR primary reformer is a key component in KBR's ammonia and hydrogen production technologies. It is typically a single top-fired steam methane reformer, SMR, designed to convert natural gas and steam into synthesis gas, a mixture of hydrogen, carbon monoxide, and carbon dioxide, under controlled conditions. KBR's primary reformer design is notable for being scalable without size limitations, unlike competing technologies that use an oxygen-fired autothermal reformer, ATR, which requires an air separation unit, ASU, and adds complexity and cost. Technip Energies, known for their proprietary TPR, Technip Parallel Reformer, technology, which enables compact, unfired parallel reformers that increase hydrogen capacity by 20 to 30% in existing plants with lower CO2 footprint and minimal modifications. Technip Energies holds a significant market share in hydrogen technology and plant supply. Casale, alongside Technip Energies, Casale offers Blue H2 by T.En autothermal reforming technology for low-emission hydrogen and ammonia production. Haldor Topsoe, now branded as Topsoe, offers a range of reforming technologies for hydrogen, ammonia, and syngas production. The primary reformer in a typical Topsoe process is a steam methane reformer, SMR, which is often integrated with other reforming technologies for enhanced efficiency and capacity. Johnson Matthey, provides advanced steam reforming catalysts and technology for primary reformers, including their LCH autothermal reforming technology. They also partner with licensors like ThyssenKrupp to offer integrated low-emission ammonia plants. Air-Liquide offers the Lurgy autothermal reforming technology and partners with companies like KBR to provide integrated low-emission ammonia and hydrogen plants. Air-Liquide is a key player in autothermal reforming technology. ThyssenKrupp supplies the ammonia process, including top-fired steam reformers with proprietary cold outlet manifold systems to enhance performance and reliability. They collaborate with technology providers like Johnson Matthey for integrated solutions. Linde Engineering, a leading global provider with over 250 reforming furnaces delivered worldwide, Linde offers a comprehensive range of primary reformer designs including top-fired, wall-fired, and floor-fired configurations. Their HydroPrime series includes modular reformers optimized for various feedstocks and applications, with integrated heat recovery and carbon capture options for low-emission hydrogen production. In summary, these technology providers cover a broad spectrum of primary reformer technologies, including steam methane reforming and autothermal reforming, with advanced catalyst, reactor design, and integration capabilities aimed at improving efficiency and reducing emissions in hydrogen and ammonia production. The industrial importance of primary reformer. The primary reformer is the main industrial source of hydrogen, which is vital for processes like hydrocracking, desulfurization, and hydrogenation in refineries and chemical plants. The syngas produced is used to manufacture ammonia, for fertilizers, methanol, and other chemicals essential to the petrochemical industry. Hydrogen generated by primary reformers is increasingly important for clean energy applications. Thank you friends for investing your time till here. Stay connected for more industry-related practices via blog mentioned in the description. Have a great day ahead.